Let's begin. Well, since we're in computational mode, I decided to skip the next section, which is more about applications and properties and stuff. We'll probably pick up with that at the end, but I just want to keep the momentum going. Let's talk about a new integration technique, something that's going to allow us to compute integrals and antiderivatives. It's called the method of substitution. So, let's actually just jump into it. This is the analog to the chain rule. This is the reverse of the chain rule. So we know we can develop integral formulas by simply reversing derivative formulas, but it turns out we can also reverse entire methods. So the chain rule was a method by which we differentiated composite functions, and substitution is a way to actually reverse this process. So the idea is, well, if we were to differentiate f of g of x, that's f prime g of x times g prime of x. So the FTC, the fundamental theorem of calculus, is going to suggest that you can integrate something like this. And the result is going to be, well, I'm going to fill in something here, something like this. Well, it's simply going to be that guy plus c. Right? Now, the question is, how do you know when you have an integral that looks like this? And ultimately, even if you know you have an integral that looks like this, how would you actually apply that knowledge? Well, you do something that's called a substitution. Pretty much, you're going to find a convenient expression here, namely g, and if we make a substitution, say a single variable for g, for example u is traditionally used, we will be able to rewrite this expression as f prime of u du, because we know that if I just replace this here, g with u, what is g prime dx? Well, that's the differential, which is du. And so by a process called substitution, I can take an integral that has this form into an integral that has this form. You should notice that this form is a lot simpler than this form. It's the first step. But then, once we figure that out, we know that the antiderivative of this is just going to be f of u by the fundamental theorem of calculus, which ultimately we can replace the u back with the g to get the final answer, right? So this process is called substitution, basically reversing the chain rule using the knowledge we gained from the fundamental theorem of calculus. Now, why is this necessary? Let's start there. Because we were computing a lot of integrals last class, yesterday. So for us, so there's going to be a general approach here. Just like we have a general approach to limits, there's a general approach to factoring, there's a general approach to all sorts of things. We can now start talking about a general approach to finding integrals. And step one will be to apply a basic rule. What's a basic rule? Well, the formulas that we obtain from reversing the derivative rule. So I'm talking about the power rule for integrals would be here. The fact that you should know that the antiderivative of e to the x is e to the x plus c, etc. All those basic ones that tell us how to find antiderivatives for specific formulas, those we can call basic rules. Okay? That's the first thing. Faced with a random integral, you're going to apply a basic rule. At least you're going to try to apply a basic rule. If you can't do that, then, as you saw yesterday, what you're going to do is try to simplify to apply a basic rule. So we had a few problems yesterday where there was this large thing, but we could just simplify by just dividing each apart and breaking it into pieces. or if there was an x in the denominator, we can bring it up and do the power rule. Just do some basic algebraic simplifications can bring us back into this space. But ever so often, this part is actually not possible. And the third thing you would try when this is not possible is substitution. Why? Because you are going to be learning a lot of integration techniques beginning in Calc 2. Substitution is going to be the easiest one. And you always try to get away with the easiest way possible before anything else, right? So it's just in the same way that if I needed to find a limit, the first thing I'm going to try is just plug in the number. Why? Because it's easy, and if it works, I get away with the easy thing. So substitution is going to be by far one of the easiest integration techniques you'll know. So it's probably going to be the first guy you look at if the basic rules don't work. And then step 4, well, there are many other steps, and that's what Calc 2 is going to be about. A large part of Calc 2 is you figuring out other integration formulas, really focusing on the antiderivative a lot. And the other half is talking about series, which the kind of things that we were talking about. Riemann sums, we want to understand those guys in more detail, and that's really Calc 2. But in the Calc 1 scheme of things, you're going to basically do these guys. Part one of the first guys you'll learn in Calc 2 is integration by parts is what it's called, and I might maybe even do a little lecture on that one. But this is the basic hierarchy. Faced with a random integral you've never seen before, you're going to try these things in this order. So now our lecture is going to be on this thing, this technique. How do you actually do that technique? And we'll go through some examples so you can see when this technique would be necessary. But let me just actually describe the technique, which is pretty much me writing out this equation that I just wrote out in words. So, if substitution seems necessary, here are the steps towards doing a successful substitution. Replace a complicating expression in the integrand with a single variable. U traditionally. A lot of kids who learn calculus in high school would even call this method U substitution because they always substitute U. It's just a traditional thing. You don't have to substitute U, but it's a very common variable to use for the substitution for whatever reason. So what do I mean by a complicating expression? Well, remember you were trying to apply a basic rule. There's going to be a reason that you cannot apply that rule. You are going to find that reason, and you're going to get rid of it by replacing it with a single variable. Now, once you do this, say 1b, there are some criteria for the thing you replace. So there are 2 criteria here. 1, this substitution must make the integrand quote-unquote simpler. What do I mean by simpler? I'll tell you specifically what I mean, i.e. look like a basic rule. Right? So you encounter something that doesn't look like a basic rule, you can't simplify it to look like a basic rule. Your goal is to make it look like a basic rule. So you're going to try to substitute someone to make that happen. Right? So this is part 1. And 2, it's very important that the derivative of the thing you substitute must be present as a factor elsewhere in the integrand. Now, of course, when you get to Calc 2, you'll learn some more advanced techniques here where if you don't have this, you can kind of put it in there by multiplying or dividing or doing, you know, the usual math trickery. But for the most part in Calc 1, you'll see that derivative staring at you in the face, and you just want to make sure that the variable part of the derivative is there at least. You can ignore constant factors here, because you can always factor constants out of derivatives and integrals, so they're not going to be, if we're off by a constant factor, it's not going to matter. So you're ignoring constant factors, the derivative should be a factor somewhere else in the integrand. So you see a complicated integral, you're going to replace an expression in that integral with a simpler expression. There must be two goals. One, you need to make it, the overall integrand look simpler, like a basic rule. Two, the derivative of the thing you substitute must be present in the integral somewhere else. If these two are not fulfilled, substitution will not work. And in fact, when you learn about more techniques in Calc 2, and you want to know which technique to choose, the inability to do this is what will determine that substitution is not the method I should be doing right now. I should try something else. These two things must work for substitution to work. If you can't get these two things to work, it's not a substitution integral. Okay. So these two are very important. Now, as far as step 2 is concerned, now you're going to make the substitution. You're going to plug in your u, and you're going to actually find this derivative, which I'm calling du, in the integral. It's very important that no instances of the old variable should remain. So you're completely changing the variable here. Three. You do this successfully, your integral will now be simpler. Simpler in the sense that some other rule or technique you already know will work. So all you have to do now, integrate this new guy. Integrate this new integral. Now, you've eliminated all instances of the old variable, which means your answer is going to be in a new variable, the variable u. For the most part, you will want to back substitute. That's what it's called. That means undo your substitution. So whatever you had replaced by u, now put that thing back in the place of u. Back substitute to get the answer in the original variable. And in general, that's the end of the substitution process. Find something that's making your integral complicated, replace it with a single variable. Make sure that this allows the integrand to become simpler and the derivative somewhere else in the function. You're going to make substitutions, eliminate the old variable. You will get a new integral that's going to be a lot easier. That was the integral that looks like f prime of u in this situation. Now just integrate because you'll have the rules to do it. Then you're going to back substitute to get to the actual answer. Now, step 4 requires some comments. So let me just make those comments here. Let me do this as 4b. Step 4 is not necessary. You can think of it as optional. If you have a definite integral. And next time I'll show you kind of how to do a definite integral using substitution, but for now I just want us to get used to the process of doing it with indefinite integrals. And I will go on further to say this is not going to be immediately apparent, but in Calc 2 you'll learn about something called trig substitution, trigonometric substitution. It is insanely annoying, and you probably want to avoid it whenever you can, and you probably want to cut down on your work as much as possible. It turns out for these integrals, the back substitution process is a whole other set of calculations that you have to do, so you probably want to avoid it whenever possible. You probably want to avoid the entire method whenever possible, but I'll talk a little bit more about that, and you'll see more about that in Calc 2. So just remember this phrase, trig substitution. Let that be now a trigger for you. So when Calc 2, when your professor comes in, okay, today we're going to cover trig substitution. I remember this. Javon said something about this. Never do this. Remember this. It's not going to be relevant for you now. It's relevant next semester. Let's do an example. And I want to show you some quote-unquote advanced techniques while using substitution. I only call them that because I didn't find out about them until after I did Calc 2, and then I was like, if someone told me this before, my life would have been so much easier. But no one told me. So I'm going to tell you guys. But first, let's do it the traditional way. So let's say you want to integrate something that looks like this guy. It's the first example. So first thing you would notice is that we do not have a basic rule that can work on that guy. Second thing you notice, there's no way to actually simplify this to make that happen. I mean, you can think, oh, well, let's write this as to the half power. Yeah, okay, that's not going to do anything. You can't multiply in, you can't expand this, at least not with a finite number of terms. So you're kind of stuck with what you have here. You also have a product of terms. There's no formula that shows us how to deal with a product of terms yet. So this guy is complicated, quote unquote. So now, the first thing you want to do is identify what exactly is making this guy complicated. What would you say? If we were to pick out whose fault is it that it's complicated. Yeah?
The 1 plus x squared.
The 1 plus x squared is making it complicated. Why? Because if that were a single variable, like radical x, that's easy. That's power rule, right? Just multiply these using laws of exponents and I can do power rule. The fact that it's a sum under the radical makes it complicated. So I would identify that expression as the complicating expression of this integral. Okay? So now my first instinct would be to say, I'm going to do a replacement here. Let u be 1 plus x squared. Okay? So that will definitely make the integral simpler to the point where the power rules should be able to kick in and help me out. So criteria 1 is satisfied. Doing that substitution is definitely going to make things simpler. Criteria 2, I need to make sure that's satisfied, which means now I'm going to take derivatives. The derivative of this guy would be that, if I do it in the differentials form. And ignoring the constant factor, so that 2 doesn't really matter to me, but other than that 2, any variable part of the derivative, the x, I need to be able to find that somewhere else in the function. And you would notice, there's an x right there. Okay, so this is a good substitution. 1, it's going to make things simpler for me, and 2, ignoring constant factors, the derivative is present as a factor in the integrand. So that means it's a good substitution. So this guy is going to work. Now, there are several ways you can approach, go on from this point. This isn't the way I used to do it, but after teaching for a while, the students tend to like this method more. I solve for the dx. So now what we're going to do is we're going to actually substitute all these things in. Okay, so that's why it's called substitution. So this guy is going to be equal to, so anything that I didn't really substitute here, these are the two things I changed. My 1 plus x squared is going to become u, and my dx is going to become this guy, but I didn't really change anyone else, so anyone I didn't change, I'll just leave them. So the 5x is there. This guy is now u, times the dx, which is here, is now du over 2x. Now what you're going to notice why we needed that derivative in here is it allows us to eliminate the old variable. I can now cancel these x's. Now we have this 5 over 2, might seem a little bit annoying, but we can factor them out. And we will be left over with that integral. Now that integral certainly looks a lot nicer than this one, but more importantly, I like this integral because a basic rule that I know can handle this integral, right? So how would I do this one? What rule would apply here? Yeah?
Power rule.
Power rule. The power rule for integration. So write this as a power. That's e to the half. Can apply the power rule. Add 1 to the power. Divide by the new power, so that's multiplying by 2/3. So that becomes 5 over 3 e plus e to the 3/2 plus c. So that's the answer. But it's the answer in terms of u. So this is what I mean by back substituting. So this is what's called back substitution. So if they ask you about something in terms of x, you should give them an answer in terms of x. So I'll do a back substitution and simply just replace the u with what it was in terms of x. So this is going to be 5 over 3, 1 plus x squared to the 3 over 2. And that is the answer. Moreover, you can even verify that this is the answer by simply doing the check. By the fundamental theorem of calculus, we can check to make sure that this is the answer, that the derivative of this guy it will give us the original integrand. It should give us that guy. Integrand. You can check by the chain rule. We actually did this. This would come down, the 3's would cancel, I'd be left with 5 over 2. This power would change to 1/2. So I'll have that 1 plus x squared to the 1/2 power, which is there. The chain rule says I'll have to multiply by a 2x. Now the 2's would cancel, and I'd be left with 5 times x times the radical. So I would get this back. So differentiating this gives me that back. So again, I know I'm right. So we have a couple checks built in here. So here we can know we're making a good substitution. And here, by differentiating, we can verify that we followed through correctly and no mistakes were made. And that process is called integration by substitution because we actually substituted expressions for old ones to get this guy to work. Any questions on this? Questions, issues, anything seems strange, out of the ordinary? So, in Calc 1, that's substitution. That's usually how I would have been taught substitution in Calc 1, and no one made me any the wiser. Here's a variation on the technique that I find, especially in Calc 2, when they're killing you with all these integrals. Any little shortcut is going to help. Any little thing that can make it easier is going to help. So here's one thing you can notice. You can actually refine your substitution to be more convenient. So for example, if you happen to be someone who isn't particularly fond of radicals, you don't want to have to deal with a fractional power, you don't have to. The trick would simply be, instead of doing u equals 1 plus x squared, you can do what's called a u squared substitution. I can throw in a square there. Why would I throw in a square there? To kill the radical, right? So I can do little things like that. And if this were a cube root, I can throw in a u cube substitution, right? I can do all sorts of things with my substitution. I can kind of mold my substitution to deal with issues that I can foresee happening, right? So if I want to get rid of a radical, let me use a square to get rid of that radical. Now, this method will require a little bit of tweaking. The difference is you have to differentiate everywhere kind of implicitly. So you don't just have du on this side, you have to differentiate this. You get 2u du. Differentiate this, you get 2x dx. So here, of course, you can solve for your dx. You'll get this is u du over x. So now, we can start to substitute these guys. Now you won't see the benefit too much on this example because still it's an easy example and I probably just do it the regular way anyway, but there are times when things get more complicated where just getting rid of radicals can make your life so much easier. So now what it would look like to plug this guy in, I would have 5x. Now here, my u is actually the square root of this guy, so this guy doesn't have any radical anymore, that's just a u. And my dx now becomes u du over x. The x cancels just in the same way it did before. And so now what I have to integrate is u squared, right? So that's a whole number power that I have now instead of like a fractional power. And if you're integrating several terms, you'll be thankful for that, right? So you don't want to have to integrate, oh, u to the 7 over 2 plus u to the 3 over 4 plus da da da. When you have a bunch of things that are fractional powers, you can just even do someone who's the LCD and then just clear all the fractions in the powers that way. It's kind of nice that you can do that. But yeah, now I don't have any fractional powers and I can easily just apply the power rule here. And now, so that's going to give me the 5 over 3, and I'm going to replace the u with what it is. Now, what you should notice here is that your u is actually the radical of 1 plus x squared. So that's what you're going to actually plug in. You're going to plug in 1 plus x squared to the 1/2. And then you get that 3 over 2 power back, which we previously verified is the answer. So a little tweak can make things a little bit nicer, which with one term it's not a big deal, but if you have several terms that you're integrating one after the other and they're all kind of complicated in their own little way, not having to deal with fractional powers is something nice. And so you should know that you're allowed to actually do that with a substitution. You can actually make these changes in real time. Here's another technique that I think comes up with substitution a lot, but they would probably not tell you about it for some reason. So let's say I can tweak this a little bit and make this an x cubed. So now, it's still the 1 plus x squared that's making this complicated. So I'd want to get rid of that guy. Okay? So here, let's say I do that u squared equals 1 plus x squared substitution. So now I want to do this check. So I'm going to find the derivative. And so now I realize that I only have an x. Does that mean the substitution doesn't work? Do we need another technique? The answer is no. So normally if you see something like that, a lot of students, the first way they think about doing it, because normally they're instructed to do it that way, they do a trig substitution for this particular kind of problem. And as I said, you want to avoid those at all costs. Turns out a regular substitution, as I've shown you, can work here. The trick is to realize that the x cubed is actually x squared times x. And so that's my x. And you might be worried, well, what about that x squared? Well, I have an equation that can tell me about the x squared. So now I can go through and I can substitute all these expressions. So ultimately now, putting this all together, I can solve for my dx here. It's going to be u du over dx over x. Now I'm going to start substituting everyone. So this brings me to, well, I have the 5, I have x squared, my x squared is going to be u squared minus 1. I have the radical of 1 plus x squared, that's actually just u. And I have my dx, which is, well, there was an x here that I missed, but I'll get it here. So that x is going to cancel with this x. And now you'd realize that I have u squared times this guy. So this integral now just becomes u to the 4th minus u squared. So I make all these substitutions and now we get that expression. Pretty easy. You can remember this problem when you go into Cal 2 and you learn trig sub. You can try this problem by trig sub and compare the methods, and you'll see who is the nicer one. Anyway, here can apply the power rule pretty easily. U to the 5th over 5, u cubed over 3 plus c, and then you can do your back substitution. Let me do it. So this would be 1 plus x squared to the 5 over 2 minus 1 plus x squared to the 3 over 2 plus c. That's your answer. And you can, of course, check that this is the answer. Find the derivative of that, you will realize that you get this verification left to the reader. So that's basically substitution with some tweaks that you can throw in here and there to make your life a little nicer. So normally, if the thing you want to substitute has an even power and what's left outside has an odd power, substitution can work. If both of them were even powers though, like if this were an x squared, then you kind of have to do trig sum, which you'll learn about in Cal 2. Like the substitution is not going to work with an x squared there, but with an x cubed it's going to work. Because I can factor off that x. So a method like this could have worked if it were x to the 5th, x to the 7th, x to the 9th. You can do a substitution. Otherwise, you need a trig sum. Okay, so that's the method with some nuances. Let me give you some examples that I want you guys to go over. Maybe we'll do a couple. We have time to get through a few of them. But yeah, like I said, just computing integrals is something you want to be very good at. You should be able to do it relatively quickly. So you do want to kind of drill kind of process here. So the best way to get prepared for integrals is just to do a whole bunch of them. Overexposure. These will get you started. So you definitely want to power through these and find more and power through those and then find more and power through those. Here's kind of a pro tip. So you do want to just work through a bunch of these, a lot of them. But when you really want to fine tune your skills and you want to know that you have substitution in the bag, one thing you can do is you can play a little game with yourself in the sense that get a huge list of integrals. So this is after you practice 100 problems, get a list of 200 problems. You don't have time to practice it all, because finals week and whatever. But you can actually, once you can actually recognize a substitution, after you've actually been through the process a bunch of times, so you know you have the skills to actually follow through on it. The more important thing is just recognizing the substitution in the first place. So this is a game I used to play by myself or with my friends. What is that game called when you have your hands like this and you try to stop it?
Slap hand.
It's called slap hand? Yeah, so I don't know what that would be called, but I guess you can call it slap integral. So we'd have a list of integrals and it'll be like, okay, we put a time limit on it. Okay, in 3 seconds I'm going to tell you the substitution here. And if not, you're going to slap me. and that's how we play it. Okay, point at this one. Okay, u equals blah, blah, blah. No! And then we move. What about this one? U equals S squared. Okay, fine. What about this one? U equals da da. What about this one? Time's up. You just, you make it fun. You don't have to use a slap. You can do whatever. You're right, just make it fun. Just challenge yourself to be able to recognize a substitution quickly. Because once you power through a bunch of them, just the ability to recognize it, you'll be able to follow through on it. And so just recognizing what method you should use is actually super helpful here. And I know a lot of people who got good at substitution, myself included, got good at it that way. We practiced a bunch of examples, but we also mentally practiced a bunch of examples. And so let's actually do that here now. Okay, so what would you substitute here? Slap! You guys are taking too long. Too long. No. What would you substitute here? Yeah? Well, you do u equals 3 plus x squared, or, you can do u cubed equals 3 plus x squared to be a little nicer to get rid of fractional powers. Okay. What would you substitute here? Huh?
ln of radical x equals...
ln of radical x could work. Ln of x could also work, so that would be nicer. Because ln of radical x is just half ln x. So I can think of this as ln x over x. And the thing is, the 1 over x is the derivative of ln. So ln is the right substitution. What would you substitute here? So you want to make the thing easier and make sure whatever you pick, the derivative is somewhere else. Yeah?
Arctan x.
The arctan. What about here? cosine x times sine 2x? No, because the derivative of sine 2x is you'd have a cosine 2x, which you don't, so that won't work. Yeah?
Sin x.
Sine of x? Why?
It's,
You have sine 2x here. The answer is sine of x, but think about it. Why? It's not directly obvious. What about this guy? What makes it complicated?
Having x squared and x cubed. Because you did x cubed plus 1. I guess you use x cubed plus 1.
X cubed plus 1 makes it complicated. Right? Because that plus 1 wasn't there, it's a power rule. Right? This expression makes it complicated. So my u would be equal to x cubed plus 1. If I differentiate that, I'm going to get an x squared. So that's a good substitution. What about this one?
X squared.
X squared equals x squared. Right? This is sine of x squared, kind of complicated. But if I let that be u, the derivative is going to be 2x, and there's the x right there. What about this one? Yeah?
1 plus radical x.
1 plus radical x would be the u. What about this one? Wheels are turning. Yeah?
4 minus x.
Equals 4 minus x. Do you see what to do here? Yeah?
Times x.
Equals tangent would be the substitution. Right here.
Plus x squared.
U equals 1 plus x squared. U squared equals 1 plus x squared, even better. What about this guy? Sine of 2x. Well, you know how to do a sine of x. The 2x is obviously what makes it complicated. So 2x would be what I choose. This one.
Like the white walls and stuff.
That one's actually a cool example. Figure it out. This one. Cosine cubed x times sine of x. What would you try?
Sine of x.
Okay, if you pick sine of x, what's the derivative?
Cosine x.
Cosine. What are you going to do with the other two cosines? Because you have cosine cubed. You have 3 cosines being multiplied here. You can get that to work. You'd have to throw in the Pythagorean identity though. Change the cosine squared to 1 minus sine squared and do that. But u equals cosine squared is u equals cosine is actually easier. Because then the derivative of that is this. Well, negative of that, so you'll get a negative over here of u cubed. So that would be nicer. So you can go through practice those. So these guys that I'm obviously whatever I don't do, you need to follow through with these. Actually practice these on your own. This one, a substitution isn't what you would actually do, at least not right away. The standard way to deal with a guy like this is to apply the half angle formula. That's actually equal to that. And to do this guy, you can do a substitution. But yeah. So the first time you see it, substitution can be a little bit tough, but especially by the end of Calc 2, you're going to be praying for substitution problems. Okay, so again, what you want to do, practice a bunch of them and then do this test again. Right? Do what I'm just saying. Just give yourself like 5 seconds to recognize it. Just randomly point at integrals and so u equals this, u equals that, u equals that, u equals that. Whatever you're not sure of, follow through with that one. Right? So you can get a lot of practice without actually going through all of the practice. But you do want a foundation, so you do want to actually do some problems first, and then you play this little game. But we'll go through a few of those next time. But you guys should, especially any ones that I told you what to substitute, definitely try to follow through with that. Make sure you know how to apply them, and we'll do some next time. Yeah. Think about it. I want you guys to. That's a pretty nice example. Because even after you do the substitution, it's a special formula that you need to remember that I'm not sure if you guys remember. Think about it. Think about it. Okay, see you Tuesday. Yeah. Easter break. Okay, have a good day.